In this problem, you are given that viscous Newtonian liquid film, which is this surrounding this circular cylinder. It is falling downward under the action of gravity, as shown in the figure. And we are also given the velocity profile inside this film by this equation. So the velocity inside this film is in the z direction. So basically, velocity here is uz, and it is a function of the radial distance r, and it is a Newtonian fluid, so its viscosity is constant, its density is given, the acceleration due to gravity is also given, and we also know it's the liquid's viscosity, and also the dimensions of the cylinder and the thin film are also given. So as the fluid film falls under the action of gravity, there is a velocity profile, and that velocity profile inside this film is a function of r. So because of that, there are basically velocity gradients, because this cylinder is stationary. So because of the no slip boundary condition, the velocity here is zero, but the liquid is flowing down. So as you go away from the surface of the cylinder, the velocity of the fluid is non-zero. So because of these velocity gradients in the radial direction, there are viscous shear stresses acting on the surface of this cylinder, which we can calculate from our Newton's law of viscosity, which tells us that shear stress is the viscosity times the gradient of velocity. So in this case, we have z velocity and the gradient is in the r direction. So we will be calculating tau r z. So from your convention for stress, you know that r, this first index, tells us which direction. So this is r direction, and the second index here tells us the direction in which the stress is acting, which is this direction. So tau rz gives us the shear stress on this r surface in the z direction. So let's find out the solution. For part A, we are asked to determine the shear stress tau rz at the free surface of the liquid. So again, tau rz is nothing but viscosity times duz by dr, and the profile for z velocity is given here. So if you find out the derivative of z velocity, you will get this to be equal to mu minus rho g by 2 mu r plus rho g b square divided by 2 mu 1 by r. So this is the shear stress acting on the fluid element. And now to find out the shear stress acting on the free surface. So if you look at the free surface, r is equal to b. So you just need to substitute r equal to b in here in this calculation. So tau rz at the free surface is equal to tau rz at r equal to b, and it comes out to be mu times minus rho g b upon 2 mu plus rho g b square upon 2 mu to 1 by r, 1 by b. So these two terms cancel out. So basically, the stress acting on the free surface is zero. You already know that it is the one of the boundary conditions at a free surface is that the shear stress acting on the free surface is zero. So that's exactly what we are recovering from this calculation. Now in the part B, we are asked to calculate the force acting on the rod per unit length due to the viscous liquid. So for finding out the force acting on the rod, we first need to find out the shear stress acting at the surface of the rod. So we need to find out tau rz at the surface, which is nothing but tau rz at z uh, r equal to a. So r equal to a is at the surface of the rod, and this comes out to be 0.2 mu plus rho gb square 0.2 mu a. Now let's consider a small circular area on this rod of thickness dz. So the force dF acting on this small thickness will be tau rz at r equal to a multiplied by dA, and dA is nothing but 2 pi r 2 pi a dz. So 2 pi a is the circumference of this circular area and dz is the thickness. So the total area is 2 pi a dz. So rewriting it again, tau rz at r equal to a times 2 pi a dz. So dividing both the sides by dz, we get df by dz, which is force per unit length is equal to tau rz at r equal to 0 multiplied by 2 pi a. So I just need to substitute this here, and F by L will be equal to rho g pi a square b by 2 square minus 1. So that's the force acting per unit length on the rod. But if you now zoom in closely near the rod, so you'll find that if you just draw a fluid element here, so the direction of shear stress on this fluid element is, this is positive r, positive z. So the positive shear stress acts in this direction, and the shear stress on this face then acts in the up direction. So the force on this rod due to the fluid will be in the downward direction. So this is the force per unit length acting on the rod, and it acts in the downward direction. Now in the part C, we are asked to set up the integral for determining volumetric flow rate. So if you remember, volumetric flow rate is nothing but area cross-sectional area times the velocity. But since velocity here changes with the radial coordinate r, we will have to basically find out a small flow rate in this kind of going through this small circular area at a distance r. So here, let's say this ring is at a distance r, then dq passing through that small ring will be u of z at r multiplied by the area of that ring, which is again 2 pi r dr. So 2 pi r is the circumference and dr is its thickness. And so integrating on both sides, you will get dq is equal to integrate from r equal to a to r equal to b, that is from the rod surface to the free surface, and in bracket you have uz, which is a function of r, 2 pi r dr. So that's how you find out the flow rate of the liquid.